My name's Ashley Brown, I'm the Chief Architect at Spider.io. Most of our business at the moment deals with internet advertising, and if you use the internet at all, which I assume you all do, this sort of thing is probably familiar to you. This cartoon sums up where we are in the industry at the moment. The reason I show that is because a lot of the things on internet adverts may be slightly suspicious. Either what they're trying to sell you or what they're installing on your computer when you're not looking. So I'll talk a bit about the company first and then go on to how we're fighting advertising fraud and advertising malware on the internet. So the company is based in the West End. We were founded in early 2010 and we were focusing on advertising fraud since about 2011. Focusing on fighting advertising fraud and not committing it. I've run that slide before without the fighting and people get a bit concerned. So what I'll cover, I'm not going to go over any code. If you want some code for Storm, then you can go to Emma's workshop in a few weeks. I'm going to go through a case study, why we picked Storm to do what we do, why we then decided to drop it, because it wasn't working for us, and then why we decided to pick it back up again. So it's a case of going around in circles, but for good reason, and I'll explain why. Can I have a quick show of hands? Who has heard of Storm before? Hands down. Who has actually used Storm for anything? Okay. Okay, quite a few, that's good. Right, quick overview. Most of you have heard of it, so I won't spend too long on this. It's a real-time stream processing framework. It was developed at Backtype. They were acquired by Twitter, so all of your trending topics on Twitter is processed by Storm, reading the Twitter feed as it comes in. It has similarities to the event streaming model used by Cascading in Hadoop, if any of you have used that. And it entered Apache as an incubator project last month, so it's now competing with Samza and LinkedIn for the Apache streaming processing award, I guess. So why did we turn up? Why did we have a need for this solution? So, the reason we get out of bed is to find fraudulent website traffic. So we collect billions of server and client-side signals every month, sift them, sort them, analyse them, condense them to let us identify automated, fraudulent and suspicious traffic. So these are different things. You've got web crawlers, they're easy to filter out. You've also got botnets, compromised computers going to websites, clicking on links, loading adverts, advertisers get paid, or advertisers have to pay, the publisher websites get paid for those adverts, they've never been seen by an actual person. So we want to get rid of that. The way we do that is to give our customers, who are ad networks and websites, access to the information they need to protect their businesses from this automated and suspicious traffic coming to their websites and faking advertising views. This means we need to clean up the data they're receiving from their analytics so they can make good business decisions. When we've done that, we also work with our partners to reveal the scale of the problem, so people actually look for solutions to eliminate the fraud. At the moment in the industry, there's a lot of almost heads in sand of, there's fraud there, but it's only 25%, it doesn't matter. What other industry would you go, 25% fraud, I don't care. Credit cards, less than 1%. Advertising, 15, 25, we don't really mind. We're trying to eliminate that, and that's why we get up, because we don't think 25% is any good. And frankly, if you're throwing away 25%, give it to us instead. So you can't really see it there. We had some coverage in the Financial Times for the hijacked PC rings we exposed. Once we've done that, we want to cut it off. Get rid of this bad traffic by cutting off their revenue. Make sure people won't pay for page views that aren't real. This means that we need to stop page view and feed back to the people that this is not real as quickly as possible before they've already gone through the process of billing it. If you look at something like the way Google deal with click fraud, is they will give you the money back next month if they detected something is fraudulent, which is fine, but imagine you have £2,000 to spend on an advertising campaign. One of your competitors makes sure somebody's constantly clicking on your advert. It's all fake. Your £2,000 has gone. You get it back at the end of the month, but because it's been used, your adverts don't get seen. So that's an excellent way of stopping your competitors' adverts ever being shown on the website, is just to use up the money they have. And you don't actually defraud anyone, because they get it back. So that's what we're trying to do. You have to be quick. So this leads us to a situation where we need an architecture that can bring in all of these signals merge them all together and get a result very quickly. We need to be able to say, is this person visiting your site good, bad, or do we not really know yet? But we have some rules. First, if a piece of software isn't helping us, we'll just chuck it out. Only jump on the bandwagon if it's going in the direction, is the phrase we use. If a piece of software comes out but it looks cool, we're not just going to use it. We need to evaluate it and see if it makes sense for us. Don't write it if you download it. This is Ben, one of our engineers. He's writing stuff. He couldn't download what we were writing on the board, so just figure it instead. So if there's an open source project that does what we need, we'll use that. This has meant we've thrown our own code out. Sometimes code we spent 6 months writing. As soon as Storm came out, we threw a load of stuff out. I'll explain how we got to that process. So, our timeline. Summer 2010, about the time I joined the company, I knew everything before that was prehistory, because I got a load of code given to me, and it was just alright, but not great. Back then we were dealing with about 60 million web page impressions a month. Barely anything. Nothing to write home about, you can process that on a couple of machines quite easily. We use RabbitMQ as a queuing server. A bit of Python deliberately sprinkled around to process the data. Hypertable as a data store, and then we use Hadoop to do some batch analysis. Nothing complicated, no big data, just really little data. That all worked for us. But there were some key events as we were going through that led us to need Storm. The first one was when we entered the advertising anti-fraud market. If you're looking after just a website, it gets, okay, a couple of million views a month, that's fine. You're doing with advertising, you're doing billions a month, tens of billions a month, hundreds of billions, depending on who you ask. They normally lie about their volumes, but they lie about everything. So we saw a 30% increase in our volume immediately, overnight, and it's very bursty, so it comes and goes. When the Americans were all looking at adverts, it comes in really quick, overnight there's not a lot there. Our existing RabbitMQ and Python worker system was all very well, but it had to scale out manually. We had to look after it, tend to it. 2 AM, alarm goes off, I have to get up, it's gone down again. I had enough of that. So we needed to look for a reliable way of distributing our code across a cluster that could expand and contract in size as the processing requirements did. Now, although Storm doesn't do that itself, it has an architecture which lets us use Amazon's AWS to spin up new nodes, add extra bits, and then shut them down afterwards. So, this is how we started. Queue server, some workers, and data store. Fairly typical architecture if you're trying to process anything. It's not that interesting. But we found that bit in the middle, these Python workers, which was code that had been written a year ago, very quickly, you know the process. All we need to get this into production very quickly. Let's write the prototype. That'll do, stick it in. That's what had happened. Doesn't scale. We went from having 2 Amazon nodes doing this to having 5, 6, 7, sometimes 20 needing to process this, and it just wasn't sensible to manage ourselves. So we had code where only 1, maybe 2 pairs of eyes had looked at it. Because code's a maintenance liability as soon as it's written, we didn't want to write any new code ourselves to look after it. It's not one of the goals of the company. No one really wants to write infrastructure software unless you're in the business of doing that. We aren't. We contribute to the projects. We're not interested in writing ourselves. At the time, we also had an in-memory database. We wanted to get rid of that, and we couldn't scale dynamically. It tried, but it never really worked without lots of blue code that just wasn't reliable. So the solution was to look at our system and look at Storm. So when Storm came out, it had the same paradigm as we did. We had events coming in streams, we had to join them together. Storm has exactly the same thing. You build topologies, which basically blocks of code you stream together. At the top of each stream, you have a queue server. You can use Kafka. We were using Rabbit because that's where our infrastructure was at the time. So we moved over to Storm for that. It means the whole community could check and maintain the code. It wasn't just 1 or 2 people looking at it. We chucked out our memory-based data store, went to HBase, because we've been used to the Hadoop stack, and Facebook had just fixed HBase so it worked. So we're happy with that. It let us keep the data for longer so that we can have better trend decisions. But we did have one problem, which was that we were using the in-memory data store to do streaming joins. We'd load all of the rows for a particular advertising impression, everything we'd see, into the database and put it back out. It's very, very good at doing that as a memory data store. But we couldn't scale that cluster dynamically because the database wouldn't allow it. Instead, we have Storm do that. Storm automatically partitions the data for you. You just give it a function to do it. It's normally just hash-based. So everything for the same impression ends up on the same AWS node. It keeps it in memory for 15 minutes. That doesn't work if you get high volumes, so then we put a data store behind it. Now this is going to sound like hard work, because I've got 15 minutes worth of data coming in, I've got to hold it in memory, flush it to disk, pull it back out. It was hard work, and it was a bit of a pain. Since then, Storm has introduced the Trident framework on top, which provides the persistent state for you. So if we were implementing it now, we wouldn't have needed to do that. This was back in the dark old days when it just been released. So if we were re-implementing again, all of this nastiness that I've just gone through, that probably doesn't make a lot of sense, is solved. So if you want to do massive joins on different data streams into one, Storm now supports that through Trident. So we sort of had this set up. Queues, then we had a scalable Storm cluster. As soon as the number of adverts being shown increased, we could increase our cluster size, introduce Storm, extra Storm worker node, and it would just scale. When they were finished, we could reduce it, and it was fine. We kept a Hadoop processing system on the sidelines, because with all of these things, if you start to get behind on your real-time processing, you either have to throw an awful lot of resources at it to catch up, or just give up. And the cheapest solution for us was actually just to give up. So if you've got, we could have a couple of thousand signals coming in a second on a small cluster, that's fine. As soon as something breaks, which it inevitably does, we then start to have queues that they start as 10,000 items long, and they're 20, and they're 50. When it gets to that point, the queue servers can't actually respond fast enough. And we kill the whole thing, switch back to Hadoop to fix the data, and just do a cold restart. So this is the way I think people are using Hadoop now. If you want to add real time, you add real time, but keep your Hadoop stuff online and ready to go, because if the real time stuff breaks, you can always go back and fix your data afterwards. And it's only with the batch processing you can really get the guaranteed view of what your data looks like. So people have been thinking about adopting Storm. I wonder how long it takes. 17th of September 2011, it was released. On the 21st, we'd already converted most of our production system to have a test cluster processing. By the 29th, pretty much everything core we had was ready to go. And on the 30th, we had all of our main Python workers that I talked about earlier, all running under Storm's control, all being distributed across Amazon AWS nodes as we needed to. Total engineers, 1. We just didn't have the resources, so we rely on open source and Amazon to do everything for us. What this gives us at the end is that within 15 minutes, we were able to get classifications on the traffic coming into websites. We can determine where the traffic's come from, how it's behaved. If it's behaved in a way we consider to be suspicious, we can flag it as such. This feeds directly back into the firewall rules and the website blocking rules for the website in question, which means they can block that traffic within 15 minutes of it occurring. So if they see it again, long sessions. One example is content scraping. If you have some data that you've paid for, flight information is an example. All of these flight booking databases, you always have to pay for that. So people just go on and scrape websites. The solution to that is to just block anything that's trying to scrape. So we provide a dashboard that gives people an overview of the legitimate traffic and all the other traffic. So the red is our weird bottish traffic. And you can see below, I've redacted it, but we explain exactly why we think it's suspicious. And all of that's generated in real time and updates during the day as it comes in. So they can make that decision straight away. So the things we learned about Storm while trying to do this is very easy to install and run. The documentation for Storm itself is fantastic. That's why we're able to get up and running so quickly, because it doesn't explain that. The documentation for the Trident part I mentioned, less good. There is an effort to improve that. I don't know if the workshop has cracked that problem yet, but you'll have to go to that and see. But Storm itself, the core bits are very good. So on a first iteration of how do you implement Storm from a previously batch-based system, or a distributed queue and worker system, is to take the core components and migrate those first. So actually in our case, we had a system where we could just strip out the middle layer. We had a queue layer at the top, data at the bottom, we just strip out the middle layer, the bit we needed to scale ourselves, and allow Storm to do the scaling for us. Second iteration, you can then provide the redundancy. We had no redundancy really in our system. If one of the workers went down, we'd lose the data that was on there, and we'd fix it later in batch. That was just the way it worked. With Storm, it provides a concept of acknowledgement of replays. So if one of your workers goes down, all the messages that were on that worker get rerun somewhere else. So we added that as a second step. Third iteration, we've got all these rabbit queue servers, which I can go back to. All of these rabbit queues, they're quite efficient because you're constantly cycling data around and around through the rabbit queue, back out into the workers, back out again. As soon as you get rid of those and let Storm handle all of the queuing, you get massive performance increase because things that are co-located they'd have to go off the box and stay in the box they're on. So that's how we came to implement Storm ourselves. Second one, suddenly we start to get customers because our system's working. 10% increase in impression volume, but suddenly all of our customers want low latency. It has to be always up, and the marketplace is very competitive. It's competitive, which means we need to be cheaper. Low latency means that we have to have data collection all across the globe, something we can't afford to do because we need to be cheaper. And the 10% increase in impression volume means we have to have a lot of components. At this point, we took the decision to get rid of Storm. What happened? So at 0.6.2, we stopped upgrading. The big customers we were bringing in just couldn't use data in real time. It was nice to have. We loved having it. It was really good as a demonstration. But actually, no one could ingest it. They didn't know what to do with it, for the most part. We say, we'll give you a live stream of all the IP addresses you need to block, or all the websites you shouldn't put advertising on. No idea what to do with it at the time. So it provided us an unnecessary cost, and all the batch options, which we could guarantee worked, and we could have much better controls on, provide better resiliency, and the cost profile is much better. Because Amazon has spot instances. So overnight, when none of their machines are being used, the price drops through the floor. You can get stuff at 10% the cost you would normally pay. That's when we do our processing. Suddenly, the cost is much better. So Storm proved too expensive to provide the low latency data collection system we needed. But we had some customers on the old system, and it continues to run. So how reliable is the Storm stuff when you get it running? For those at the back, you might be able to see, 579 days is the uptime on our active topologies. There is one at 389 days, which is a little bit disappointing, which I kicked over. Once they run, it just runs, and this is why we've not touched it. This is 0.6.2, which was released in 2012 or so, just, well, 579 days ago, I guess. Just let it go. So then what happened? Well, let's plug this rabbit thing, legacy. Leave rabbit, leave Storm. Suddenly, Hadoop is back on the table. But we decided to stick with the cascading framework. Everything in Storm is event stream based. We wanted to have the same code base shared between them so we could chop and change. The cascading framework provides the event stream model for Hadoop. So we have a layer in between Storm, Hadoop, and Storm cascading in our code that lets them work with both. So our core processing can work on either of the event streaming systems, and we could add any others that we wanted to. As a result of changing to that system, suddenly we're able to crunch much more data reliably and repeat it. So we managed to identify a big cluster of computers on US IPs, got international press when we said, look, this is a real problem, you do need to deal with this. We've got many other sources of fraud under investigation, and using Amazon EC2 dropped our costs dramatically because you can do the batch processing at night, not during the day. The lesson we learned from that was that the benefit of real-time processing was a business decision. Nothing to do with how good the technology was. The technology was there, we could use it. But the business said, we can't afford to do this. So batch was more cost effective. The Storm is easy and reliable to use, but you need to remember you have infrastructure around it. The core Storm bit is fine, but if your queue servers or your data collection service feeding data into it go down, you've lost. And for us, data collection was so important that we used Amazon CloudFront as a content delivery network. That's how we collect data. We don't actually collect data ourselves, we let Amazon do it and send us the logs. So for us, look, it might be the supporting infrastructure around it that gives you the problems, and that's what we found. Storm was good, the rest of it was unreliable because it hadn't had the effort put into it as Storm had. So then, number 3, we go from hundreds of millions to billions and billions and billions. Suddenly it's an arms race. So we keep going, you need to sort your fraud problem out. This is what these people are doing. Within 24 hours of us announcing this particular botnet, everyone benefiting from it shut down advertising. There were websites that were clearly defrauding by putting adverts on, and their sole purpose was to have adverts that infected machines visited. So they got paid for the adverts on their website, and they were running botnets, possibly. We don't know that, but someone was certainly paying for traffic for it. Then the advertising on that website disappears. They have to come up with a new way. So, we were delivering block lists within 24 hours, 36 hours. That was pretty good. That's absolutely no good when you're in your arms race and you need to block straight away. So the sources and signatures of fraud change faster. Things like user agents changing. They changed their user agent, their fake user agent, from being IE10 to IE11. Okay, well done, that's fine. We can cope with that. But when they get more subtle changes, you need to be able to account for it. And suddenly we're getting a growing demand for people for immediate classifications that we can provide in 36 hours. They wanted it within 15 minutes, within half an hour. This is a familiar story, we don't really know how to do this. So it's now Storm comes back. So this is where we are now. We've gone from a situation where no one had a clue how to use the real-time data to where they desperately want it, because they know that in order to stop selling adverts to basically computers under their own control, they need to block things straight away. So we're returning to Storm, paired with the Hadoop libraries, to let us do clustering and various other machine learning tasks in real time as the data comes in. So we can update our models and update our fraud detection as things come in. So we're crunching billions of impressions at the moment using cascading in Mahad. As I said, we can switch between cascading and Storm, so when people are willing to pay us the correct amount of money for real time, we switch from cascading back to Storm. So we'll be able to give them a real time response and let them block before the advert is even sold to people. Is the next one. An advert comes up, people say, do you want to buy this? No, everyone will know that it's a bad advert to buy. So I said this is sort of a case study and a story, a bit about our company, a bit about how we changed architectures as we went through and why. As the business changes, your architecture has to change. If you're thinking of choosing Storm for something, you've got an existing event streaming system that could use resiliency. Storm is excellent. Your business needs new real-time performance like we do currently, some sort of new analysis component that would work with event streaming, go for it, it's excellent. If you're happy to run the infrastructure around it, go for it. If you don't have any need for real-time data, don't use it. And don't use it just because it's cool, and it is cool, Storm is cool. It's from Twitter, it must be cool. We also found using cascading for Hadoop jobs and Storm for real-time is really handy because you don't have to change the paradigm in your head. It's all event streaming. Just think of everything the same way with joins on event streams and you're absolutely fine. In some circumstances we share code and we've got some libraries that will provide common components between them. And so, as you saw, a reasonably managed Storm cluster will stay up for absolutely ages, nearly 2 years in our case, and I expect it to still be running in exactly 2 years. So that's the end of that. I hope that was useful for anyone thinking of going to Storm, or maybe why they should choose it or why they shouldn't. I'll take any questions.